Precalculus with Larson, Lesson 15, Chapter 2.7, Graphs of Rational Functions. All right, what we're going to learn here is how to analyze and sketch graphs of rational functions, how to sketch graphs of rational functions that have slant asymptotes, use graphs of rational functions to model and solve real-life problems. All right, so down here they had another parent function they wanted to introduce you to. The parent function is y equals 1 over x. It has a horizontal and a vertical asymptote. The horizontal asymptote here is y equals 0, and the vertical asymptote is x equal to 0. And it gets close to it, but it never crosses it. Notice there's no y-intercept and there's no x-intercepts at all. There's none. There's no intercepts. The domain going left and right has everything except that 0. It's undefined at 0, so the range in the domain were all the numbers except for 0. So negative infinity to 0, print C, union of 0 to infinity. It's decreasing on all of it. When you go, again, left to right, as you go left to right and you follow the roller coaster here, it goes down. And then when you jump up to here, it's still going down from left to right. So it's decreasing from negative infinity to 0 and from 0 to infinity. It's an odd function. Again, odd means if you have a point x, y on the graph. It also has the point negative x, negative y on the graph. So here's the point 1, 1. So you also have the point down here, negative 1, negative 1. Any point here is also down here. Just change both the signs. All right. So we'll get right into it here, doing some graphing, which is what we worked on yesterday too, on the other lesson. So what I taught you to do, the first step is always to factor all of it. So factoring all of it, the bottom needs factored. The top is already factored in the 5 times x plus 4. So factoring the denominator here, it factors in x plus 4 times x minus 3. So we'll start with the denominator. What makes the denominator equal to 0 for vertical asymptotes? And notice the x plus 4 cancels out. So we have a hole. There's a hole at x equal to negative 4, and then we still have that left over. We still have left over 5 over x minus 3, even canceling out the hole. And so we have a vertical asymptote at x equals 3. And again, that's from setting that equal to 0 and solving it. X minus 3 equal to 0 makes x equal to 3. Likewise, x plus 4 equal to 0. Move the 4 over and it makes it negative 4, so there's a hole at negative 4. And then while we're there, looking at the hole, so if x is negative 4, let's find the y to find exactly where the hole is at. So plug it back in here. Do f of, well, it's a g. So do g of negative 4. So that makes 5 over negative 4 minus 3, or negative 7. So the hole is at exactly, I'm running out of room there. The hole is at negative 4, negative 5 sevenths. All right, and then the horizontal asymptotes, again, look at the highest power on the top, and that's the 1 here. So that's 5x. And on the bottom, the highest power is x squared. So it's bottom heavy. There's more x's on the bottom than the top, so I call it bottom heavy with x's. So when it's bottom heavy, the graph approaches, as it goes to 0, as it goes to infinity, it approaches 0. Because what you can do when you clean up the x's on it, it is 5 over x still when you cancel out one of the 2 x's in the denominator. So as the graph approaches infinity, 5 divided by infinity gets super small, and it gets closer and closer to being 0. So we've got the horizontal asymptote y equals 0. And then we've got the vertical asymptote of x equals 3. So label it. So I labeled it x equals 3. I labeled that y equals 0. I've got a hole at, what did I say? -4, -5/7. So right there is my hole. All right, so at this point, let's just put it in the calculator. So we have on the top, I'm going to do a parenthesis around the whole top. So I had 5 and then parenthesis x minus x was x plus 4. Close the parentheses up and then divided by parenthesis x squared minus x minus 12. Graph. So you graph the original equation on it, not the new one. Oh, I put something in there wrong. That's not what it's supposed to look like. What did I do? Let's see. 5x plus 4, x squared minus x minus 12. Huh. Oh, it was a plus x. I drew right over that thing and it made it look like it was a minus. Son of a gun. That was a plus. All right. There we go. That's more like it. Okay, so getting some numbers off the table there. Go to second graph. Let's see. Oh, let's use that one. -2, -1. That would be worthwhile. We had 2, -5. I think that's enough over there. Let's go a little higher here. At 4, it's 5. And see, and at 6, it was 1.67. That's enough. All right, so connecting it up here, making it look nice. Here we go. All right, looks good. It didn't have, oh, it did have an intercept. Son of a gun. There's an intercept over here. Let's make sure we plot it right. So let's go to the table. At the number 0, it was -1.67. Oh, I did not hit that point. There we go. All right, so if you have an eraser, erase that. You have to hit the intercepts. And I didn't hit that intercept, so I had to go back and fix it. If there's any x or y intercepts, you have to hit it, or any max or mins, hit those. All right, now it's better. Now I get all my points. All right, next up, we are going to do slant asymptotes. Yay! I love slant asymptotes. You find slant asymptotes by dividing. Here's a slant asymptote right here. So it's oblique. They also call it an oblique asymptote. And this is, of course, the vertical asymptote. And again, to find slant asymptotes, we're going to have to divide. And when you divide, the part you get when you divide is the slant asymptote. We don't care about the remainder. We just care about the piece you get when you divide. Oh, and back here, it gave a good definition of when you have them. So when you have a slant asymptote, if the degree of the numerator is exactly one more than the degree of the denominator, then you've got a slant or oblique asymptote. So if the top is one more than the bottom. So this one's got a slant asymptote because the degree on the top is x squared, and the degree on the bottom of it and the denominator is x. And so that's exactly one more than the bottom. The numerator is one more than the denominator. When that happens, you need to divide and find the slant asymptote. All right, so we're going to divide x into, we have -x squared. There was no x, so I'm going to put 0x and then plus 1. So divide the bottom into the top. And so when you divide x times x squared, I'm going to need a -x. It makes that -x squared. So subtract that's gone, bring down the 1. And of course you can't divide x into that. So the whole answer is just y equals -x. That's the slant asymptote. Now it's in y equals mx plus b form. It's a line. We're drawing the equation of a line here. Just like we did the vertical and the horizontal asymptotes, they were lines. So it doesn't have a y-intercept. If you think about it as y equals mx plus b form, there is no y-intercept, no b, so it goes through 0. And it's got a slope of negative 1 over 1. So down 1, right 1. So I'm going to draw a dashed line through it for the asymptote. So label it y equals negative x. And then, so that was, and again, I didn't say it, but you're not going to have a horizontal and a slant asymptote. You have one or the other. So since we have a slant asymptote, there is no horizontal asymptote. You're not going to have both. And we do have a vertical asymptote because the denominator, again, you look at where the denominator is equal to 0, and it's equal to 0 when x is equal to 0. So x equals 0 is a vertical asymptote on this one. So x equal to 0. So let's draw that. Okay, and put in our calculators. There it is. It looks pretty. There's really not many points really to bother even getting on this. It gets so close to that line, y equals negative x. Matter of fact, I'll even just put it in there to show it to you. Y equals negative x. And in front of the y, I'll make it a little darker by hitting enter. Look, it comes super close to it. So we might as well just draw it. So it comes really close to it over here. I think it might go through 1, 1. Let's look. Let's see, 1, 0. Yeah, it goes through 1, 0. So that's the x-intercept. Oh, I didn't get that close to it over here. That's a sad story. So try to get really close to the line. And then on the other side, we have negative 1, 0. And again, it gets really close to it, but it never crosses it. All right. We've got one more to do on the next page. Okay, so on the next page, this one also has a horizontal asymptote because it's one more on the top than the denominator. Here's the highest term on the top and on the bottom. So you've got 2x squared over x, so that makes it a horizontal asymptote. Because again, the top is 1 greater than the bottom is. So we're going to divide. So x minus 2 into 2x squared minus 5x plus 5. So to get 2x squared, that's times 2x. And then 2 times negative 2 is negative 4x. Subtract. And so that makes negative 5 minus negative 4, or negative x. And then bring down the 5. So then to get negative x, we need negative 1. Multiply both of them by it. So it makes that negative x plus 2. Subtract. And again, all we care about is what's on the top here, what we got when we divided. We don't care about the remainder. So y equals 2x minus 1 is the slant asymptote. So again, the y-intercept's negative 1. The slope is 2 over 1, so go up 2 over 1. I'm going to connect that with a dashed line. So y equals 2x minus 1. All right, and again, you can't have a horizontal and a slant asymptote. So there's no horizontal asymptote. And then looking at, so that takes care of, let's do the vertical. So the vertical is what makes the denominator equal to 0. So when x minus 2 equals 0, so that's x equals 2. So that's the vertical asymptote. And technically, you were supposed to try to factor the top and see if it canceled out and made a whole, but spoiler alert, it doesn't. So we're all done with it. All right, so let's put it in the calculator. Clear it out. So we have got, in parentheses on the top, 2x squared minus 5x plus 5, and then divided by, in the denominator, x minus 2. Hit graph. Okay, notice we have a relative max here and a relative min there, and I want to make sure I hit those spots. You're supposed to hit any intercepts, and we do have an intercept right here. Let's get that intercept real quick, because that's going to be on the table. That's at 0, negative 2.5. So we'll label that 0, negative 2.5. All right, and so let's grab the max here from the graph. We need that max and that min. So that max, second calculate the max. All right, Mr. Spider is already to the left, so I'm going to hit enter. Go over the hill, go all the way past it. It doesn't matter how far you go. And the max is at 0.77, comma, negative 1.9. So 0.77, negative 1.9. So we'll label that 0.77, comma, negative 1.9. Or you could write it on the graph. It's just hard to see it on here, so that's why I wrote it over to the side. All right, and then let's find that minimum on the other one. Oh, see, it's hard to see up there, so I'm going to change my window and take it, for the Y max, take it up higher. Maybe we'll go up to 15, and that was under window. Now I can find where that minimum is at. So second, calculate the minimum. So just go to the left here with it, and it'll pop up on the other side. So enter, go over it then, all the way past it. Enter again, and the minimum is at 3.22. 3.22. I'm just going to put it on there. 3.22, 7.89. Right there. And look, I drew it and then I missed it. What is that about? Okay, so again, that point was 3.22, comma, 7.90. All right, so let's see, and we have our one intercept down here. I think we got everything. That's it. All right, well, thanks for joining me. I'll see you again.